Nuclear magnetic resonance spectroscopy, or NMR spectroscopy, is a powerful technique that can be used to determine the structure of organic compounds. A sample of the organic compound to be studied is placed within the NMR spectrometer, and a reading known as an NMR spectrum is produced. To understand NMR spectroscopy, we need to describe how NMR spectra are generated, understand and interpret NMR spectra. Once the sample is placed into the NMR spectrometer, a magnetic field is applied to the sample. The sample is surrounded by a source of radio waves and a radio receiver. The presence of a strong magnetic field and radio frequency radiation generates an energy change in the nuclei of atoms in the sample and causes them to switch between the two different spin states. This is called resonance. The frequency of radio waves required to cause this switching between spin states for a particular magnetic field is called the resonant frequency. The resonances are detected by the radio receiver, and information is fed to the computer. A spectrum is produced. This is a graph that shows the energy absorbed by the radio receiver on the y-axis and chemical shift on the x-axis. Chemical shift is related to resonant frequency. In proton NMR, the hydrogen atoms attached to different functional groups within the molecule react differently to the magnetic field. Let's have a look at the proton NMR spectrum of ethanol. The first thing to notice is the TMS peak. All chemical shift values are measured by reference to a standard. This is tetramethylsilane, known as TMS. The chemical shift value of the hydrogen atoms in TMS is 0. TMS is added to the sample to calibrate the spectrum. There are two other peaks shown in this spectrum. This shows that there are two hydrogen environments present in the substance. We can learn more about these by looking at the heights and chemical shift values of the peaks. In general, the further away a hydrogen ion is from an electronegative atom, such as oxygen, the smaller its chemical shift. The peak on the left is likely to show an environment that contains an electronegative atom, such as oxygen. From looking at the heights, we can see that one peak represents one hydrogen atom. The other peak is 3 times higher. The more hydrogens that have the same chemical environment, the higher the peak will be. This peak represents 3 hydrogen atoms. If we look at a molecule of ethanol, we can see which hydrogen atoms are responsible for which peak. There are 2 different hydrogen environments in ethanol, the methyl group and the carbonyl group. There are 3 hydrogen atoms in the methyl group. These are responsible for the peak at chemical shift 2.2. The single hydrogen in the carbonyl group is responsible for the peak at 9.7. If we zoom in on the NMR peaks, we can see that they are often split. This split occurs because the hydrogen spin interacts with the spin states of nearby hydrogen atoms in different environments. The splitting of the main peak into subpeaks is called spin-spin coupling. This splitting gives information about the neighbouring hydrogen atoms, which can help us to work out the structure of substance. The table shows the split patterns that occur when different numbers of hydrogens are located on adjacent carbons. This is illustrated with the N+1 rule. In ethanol, the single peak at 9.7 showing the hydrogen in the carbonyl group is split into 4 subpeaks by the presence of the 3 hydrogens of the adjacent methyl group. The peak at 2.2 showing the 3 hydrogens of the methyl group is split into 2 by the presence of the 1 hydrogen on the carbonyl group. The important things to remember about NMR spectroscopy are: Chemical shift values can be used to give an idea about the hydrogen environment. The size of the peak tells us how many hydrogen atoms are in that environment. The presence of hydrogens on an adjacent carbon atom will split the peak into n+1 smaller peaks.